Hello, I'm the medieval Mr. Daycock, and today I'm going to be teaching you about the product rule for differentiation. So what is the product rule? The product rule is what you get, or what you need to use when you've got a derivative like this. We've got y equals a product of two functions, sine x and the natural log of x. So how do we find the derivative in that case? Well, I'm going to demonstrate this using a pictorial method. So imagine a rectangle. Very complicated thing to imagine here. And the rectangle has side lengths of u and v. And why are we going to do this? Well, we need to think about functions where y of x is equal to something like u of x times by v of x. Two functions of x being multiplied together. And so, therefore, the inside is y. The area of this rectangle is our y. But these are functions, so they can vary. And that's what we're going to do. We're going to add a little bit of a change, just a very tiny change here. And we'll call that delta u. That's our little tiny change in u. And that's going to make the rectangle a little bit bigger, or possibly a little bit smaller. Equally, I'm going to add a very tiny change here of v, delta v. That's going to make it a little bit bigger this way. And also, we're going to get a little bit on the end here because we made it bigger in both directions. And so if my delta u and delta v are very, very small, we just get this very, very slight increase in the rectangle. And we are left with basically a slightly larger rectangle or a slightly smaller rectangle. But importantly, this extra bit, this little bit that's been added on, in black like this here is our delta y, because it's the change in the whole area of the rectangle. So that there is delta y. The change in the area, that little bit of extra area that's been added on. Well, now we just need to work out what that area is. Well, delta y is equal to three different bits. This red bit here, which is v, the height of it here is v, and the base is delta u, so the change in y is v times by delta u, plus the blue bit up here, and that's got a length of u and a height of delta v, so plus u times by delta v, that's the change in area of the little rectangle, the little strip on top, and then plus that tiny little, not square, but tiny little bit extra, which is going to be just delta u times by delta v, and that is this little bit up here. That's our delta u times delta v. So our change in y is equal to v times by delta u plus u times by delta v plus delta u times delta v. Now, to get a derivative, well, we need to think of this change in terms of x. We think about our derivative as a gradient, and so what we're really thinking about is what we want is delta y divided by delta x, i.e. the change in y divided by the change in x. But if I divide that by x, I need to divide everything on the right hand side by x, so we're going to get v times by delta u over delta x plus u multiplied by delta v over delta x plus delta u times by delta v over delta x. Okay, and now what do we want? What do we want for it to be a derivative? Well, we want that change to be as small as possible. So we want to take the limit as the change, this is incorrect notation, but close enough, we want our change to tend to 0. And if we let that happen, we're going to get dy by dx rather than delta y by delta x. dy by dx is equal to v multiplied by du by dx plus u multiplied by dv by dx plus, well, we are still going to get dv by dx, but the delta u is going to tend to 0. So it's 0 times that, and so this bit disappears entirely. And so now we have our product rule, that dy by dx is equal to v times by du by dx plus u times by dv by dx, if we can write y is equal to uv for some functions of u and v functions of x. Another way people often write this to make it look a little bit simpler is if y equals uv, then y dash is equal to u dash v plus v dash u, just to make it a little bit nicer and a little bit faster to write down. Now, how do we use this? Well, here's exactly the question we're dealing with. We've got y equals sine of x, natural log of x. So I'm just going to say u equals sine of x, v equals the natural log of x, and therefore, and it's always nice to have it as a nice little grid, u dash equals cosine of x, v dash equals 1 over x, and then we've got a nice little grid here, and we sort of multiply along the diagonals because we want u times by v dash and v times by u dash. So we multiply there and we multiply there, and we're going to get that dy by dx is equal to sine x multiplied by 1 over x plus cosine of x multiplied by ln of x, natural log of x. And then arguably slightly simpler way to write it would be dy by dx is equal to sine x over x plus cosine x ln x. And we're done. Okay, second problem along a similar vein. Find dy by dx when y equals 5 cosine of 3x e to the 2x. So again, we just pick our u and our v. So we're going to pick u is equal to 5 cosine 3x. And we're going to pick our v is equal to e to the 2x. And then we just differentiate each of them. U dash is equal to, the derivative of cosine is negative sine, and this 3 needs to come out, minus 15 sine of 3x. Make sure you agree with that, make sure that makes sense to you. And then v dash is equal to 2, the 2 comes out, e to the 2x, because e differentiates to itself. And therefore, dy by dx is just equal to the diagonals again. So it's going to be 5 cosine of 3x multiplied by 2e to the 2x plus, and then we go for the other diagonal, negative 15 sine of 3x multiplied by e to the 2x. And then we simplify, so we get dy by dx is equal to 10, 5 times 2, cosine 3x e to the 2x minus 15 sine 3x e to the 2x. And then we can do a little bit of factorizing, make it maybe look a little bit nicer. That's equal to 5e to the 2x lots of 2 cosine 3x minus 3 sine 3x. And we're done. Okay, that's the product rule with a couple of examples. Thank you for watching, and I'll see you in the next video.